Everyone, welcome back to another physics session. I hope you had a nice evening. Today's physics session is on density and states of matter, although we're going to be starting with a nice recap of the space topic that we've just covered. If you don't know me already, my name is Preshayla and I study physics at Loughborough University and I've been tutoring for 4 years. As always, these sessions are an hour long, and if you do have any questions throughout, please put them on the Q&A function or the chat function, and I will try to get to them as quickly as possible, or just leave them to the end, and then I'll do my question session at the end anyway. So what we're going to cover today is a nice long recap of space, make sure everything's consolidated because it was quite a short topic, which we only did in 2 webinars. And then understand the equation for density, understand the ways in which we can measure the density of a solid and a liquid, know the structure of the states of matter and the processes to switch between them, understand the kinetic theory of matter, and know how to find melting and boiling points. Then we'll have our example questions and time for your questions at the end. As always, this webinar is recorded, and if you want to watch it back, if you didn't catch anything, or if you just want to refresh and revise, then they will be on our YouTube channel. Okay, so we're going to start off with everyone's favourite time of the day, which is the quiz. So you guys were asking for a quiz yesterday, so I thought we'll do a nice space quiz to kind of wrap up the topic. Same style as last time if you were here. If you weren't, you need to go to this website, joinmyquiz.com, and type in the game code. I will put the link on the chat for those of you who need it. And yeah, just enter as soon as you can, and then we can get started. So that's the link if you guys need it on the chat. You can join from your smartphones or your laptops, computers. Cool, already got the first one in, and there's 22 of us today, so let's try and get as many as possible in. There'll be roughly 15 questions, and they will be all multiple choice and 20 seconds to answer each. Okay, we've got 14 of you in, so let's try and get that up to a few more. If you can't access the link for whatever reason, if you can't get into the room, then I will put the questions up and you can kind of follow along. Okay, we'll wait for the 17th person and then we're gonna start. So let's see if we can get 17 people on. Perfect. Right, let's start. If you guys haven't had a chance, then the link is on the Zoom chat and you can access it there. I'm going to mute the music. Sorry, guys. It's just really loud in my ears. Here are the questions if you guys can't see them. Some of you nearly at the end. And this quiz can be reattempted as many times as you guys like. So if you do want to have another go at it, for example, after the webinar, then you can, and you can play with your friends or whatever. Really good, guys. We've got it back up to 70%. Let's try and keep it there. Okay, some of you getting really close to the end now. And we've got all of our participants on. Okay, I'll give us 2 more minutes. Well done. Let's try to keep it at 71%. That's really good, guys. Don't worry if you got a few questions wrong. I'm going to go through the answers and we're going to recap anyway. Well done to PC, S and M, who are first, second and third. Okay, and we'll stop there. So let's go through our questions. So this one was pretty well done. What is a cloud of dust that a star can form from core? That's a nebula. All stars start off as a nebula. During the main stable period of a star's life, what is a star? So the main kind of gives you the clue here, and the stable period is the main sequence period. What process occurs in stars? Is it fusion or fission? That would be fusion. So stars are constantly fusing elements to keep their energy burning. How many planets in our solar system? That is 8. And the closer you get to a star, the gravitational force. So the closer you get to a star or planet, the stronger the gravitational force. What dictates when a main sequence star leaves the main sequence? That would be when it runs out of hydrogen. Elements heavier than iron cannot be produced by a main sequence star. They need more energy to be produced, and so a supernova would have to produce them, not a main sequence star. What is the force that keeps planets where they are? This one was a most well done question, and that would be gravitational attraction. That's absolutely correct. What happens if a planet gets too close to the Earth? Okay, we will go through this in a second, but if it gets too close to the Earth, it starts being pulled in by the Earth, which means it slows down and starts spiraling in and may hit the Earth. What's the key feature of a geostationary satellite? It stays at the same point above the Earth at all times, okay, so that it can constantly survey that area of the Earth for weather, for communications, for whatever purpose. If a galaxy is said to be redshifted, its wavelength gets longer. Really well done, guys. That is probably the hardest part of space, redshift. So well done. And the same for blue shift, wavelength gets shorter. The name given to the energy produced from the Big Bang, that's cosmic microwave background radiation. So make sure you get it in the correct order. And dark matter accounts for what percentage of the universe? That's 27. Okay, so well done to, let's have a look at the final leaderboard. Well done to all of you, really good attempt. We got 75% accuracy in the end, which is great. Well done to Fab2, PC and Zai, who were top 3, and it looks like you got all the questions correct, so well done. So let's quickly go through our space module. So solar system, we know has one star. Our star is called the sun. We have 8 planets in our solar system. We have natural satellites, which are called moons. So the Earth has a moon, but Mercury and Venus don't have moons, and some planets have more than one moon. The galaxy that we belong to is called the Milky Way, and other things that are in our solar system are comets, which are frozen rocks, meteors, which are small bits of rock, and dwarf planets and asteroids such as Pluto, and kind of failed planets that didn't quite make the size that is needed to become a planet. Then we talked about the star life cycle of a star that is quite kind of close to the size of the sun. So the particles in the cloud pull together under gravitational attraction, and the particles speed up. We get denser, we get hotter, and we become a protostar. Denser and collide even more, we get even hotter. The gravitational potential energy is being changed into thermal energy, which makes the star burn. And if it does get hot enough, hydrogen starts to fuse, and we get hotter and brighter, and the star starts to shine. So that's how we get a shining star, but this is the life cycle of a star. So if we have stars that are about the same size as the sun, we're going to go from a nebula to a protostar, main sequence, and then down this side of the diagram. And if it's much bigger than the sun, we go down this side. And you can see that a supernova will either go to a neutron star or a black hole, both of which are very dense objects. So main sequence stars are these stars which are in the main stage of their life. They're stable, they're good, they're constantly giving out energy, they're constantly fusing hydrogen to create helium, and they're nice and stable. The outwards heat radiation balances the inwards gravitational force, which means that they're stable. So because those forces balance each other, they are stable. And then we talked about the production of our elements. So the elements that are in our Earth today all came from what we think was the Big Bang. And fusion processes in our stars are what is creating these elements. But elements that are heavier than iron are produced in supernova, okay, because more energy is needed to produce those elements. However, elements that are lighter than iron will just be produced in a normal main sequence star. That's absolutely okay. And the explosion of the supernova is what distributes those elements throughout the universe. So then we started to talk about planets, satellites, and orbits, and the force that keeps planets or satellites or stars where they are. So we know that the force that keeps them where they are is this gravitational force. And because we have this force, we have a resultant force on our planet. Now that force acts towards the center of our planet, the center of the circle. So you can see on the diagram, the force of gravity is a force which acts towards the center of the circular orbit. Okay, so it's an inwards force. It acts towards the center of our circular orbit. Now, because it acts towards the center of our circular orbit, it's called a centripetal force. Okay, so a centripetal force is this new key term that we need to know, this new type of force, which is created by the gravitational force, which acts towards the center of the circle. Now, one really important fact that we need to know about that is that motion is constantly perpendicular to force. So we can see that the planet's motion here goes out this way. So the planet is going around the circle and its force is at a right angle to that. So in an exam, you may have to draw on arrows of direction and for motion and for force, and you know that they must be perpendicular to each other. Now, one last important fact about orbits is that if we have a circular orbit, we know that the planet always changes direction. Yeah, so it's going left, it's left, 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 and it's always changing direction. So we can see that the arrows are constantly changing. Yeah, so it's going in a circle, just like a car in a roundabout constantly changes direction. But that planet has a constant speed. Okay, the planet has a constant speed. And if it has a constant speed, but a changing direction, it has a changing velocity. Because remember, velocity is a combination of speed and direction. And if one changes, the whole thing changes. So if direction changes, velocity changes, although it's still going the same speed. Then we thought about, okay, what if it gets too close to the Earth? So you can see that if it gets too close to the Earth and comes in under this black dashed line, which is its correct orbit, the atmospheric drag from our Earth will start to pull it down. And it starts to pull it down and slow it down. And if it gets too slow, it starts to spiral in. It won't stay in its orbit anymore. But if it becomes too slow for whatever reason, it will spiral in and hit the Earth. If it's too fast, it will ping off into space, neither of which we want. So it's very important for astrophysicists to get the correct speed for our orbits. Okay. And if we want to keep it at the same height, we need to get a certain speed. So geostationary satellites are an example of a satellite which needs to stay at a constant height above the Earth. Geostationary satellites are really important for communications because they stay at the same point on the Earth. So the Earth is rotating and the satellite is moving at the same speed that the Earth spins and in the same direction. So if it travels in the same speed in the same direction, their orbits constantly match, which means that the satellite is constantly at above the Earth at the same point all the time. Okay, so very important for communications and kind of cellular networks. So that's basically how our phone works. It picks up the signal from the satellite and the satellite kind of transports it back down. So very important for communications, and that's a very kind of specific use of satellites. More generally then, for using satellites, the further away from the sun, the less speed we need for it to orbit, because gravity is weaker further away from the planet. And therefore, if we're further away, it takes longer because the circumference is bigger. And the way that we can work that out is time equals circumference divided by speed. So we know that the orbit takes longer if the circumference is bigger. So if the orbit is bigger, if it's further away, it's less speed, but it takes a longer time. Okay, and that is worked out by this equation, but it's not a formal equation. It's just a variation on speed equals distance over time. Then we went on to talk about redshift. So redshift is this idea that can help us to understand whether a star is moving towards or away from the Earth. Light waves are stretched out if the star is moving away. Wavelength is increased and it is redshifted because it moves to the red side of the spectrum where wavelengths are longer. Same is true for the opposite scenario. Light waves are squashed together if the star is moving towards us. The wavelength is reduced. Because the wavelength is reduced, it shifts to the blue side of the spectrum, and that is where the shorter wavelengths are. So that's redshift. But how do we know? So spectral lines. Spectral lines are these lines that show up due to the absorption of light at certain wavelengths by specific atoms. So this may be a hydrogen spectral line spectrum. And the hydrogen only absorbs the light in these specific wavelengths. So a little bit of blue, a little bit of yellow, a little bit of red. And then we find that the light from the galaxy shifts that light. Okay, it shifts that light towards the red end of the spectrum. And that's how we know that the light has been redshifted, because of these spectral lines. So the position of the lines tells us whether there's been a blue shift or a red shift. And the bigger the shift, the more the waves are squashed. And the faster the star moves, the bigger the shift. Then we went on to talk about Hubble's findings. So Hubble found that the light from the distant galaxies, so on the edge of our universe, was being redshifted. And therefore, he concluded that the distant galaxies at the edge of our universe are moving away from the Earth. But he thought, okay, well, it's not just that they're moving away from Earth, they're moving away from everything. So we know that the whole universe must be expanding. And the greater the galaxy was away, the faster it was moving. So we know that the universe must be expanding. This was the evidence that Hubble gave for the universe expanding. Then we talked about the Big Bang Theory. The Big Bang Theory is this idea, this model, that the universe started at a very small, hot, dense point and exploded suddenly and started expanding. All matter was sent outwards by this explosion. And one thing that kind of gives us evidence for the Big Bang Theory is this idea of CMBR, or cosmic microwave background radiation, because we know that if there was this huge explosion, then there must have been some energy created, some really high energy electromagnetic radiation. Well, we know that that is gamma rays from our electromagnetic spectrum. And so scientists have looked for gamma rays in our Earth, and they found it in the form of cosmic microwave background radiation. There is radiation on our Earth that cannot be explained. And so we've said that this radiation must have come from the Big Bang, and it's still here today. So we went on to talk about the future of the universe. Will it expand forever? Well, it depends on how dense our universe is, how densely packed are our stars and our galaxies. But stars in a galaxy only account for a very small percentage of that galaxy. So our Milky Way, for example, our Milky Way galaxy, only a small percentage of our galaxy is actually filled by stars. The rest of the mass is unknown. And the reason that we know this is because if we were to only have stars in our galaxy, only the things that we can see, our galaxies should be spinning a lot faster, but they don't. They spin much slower than we expect, and therefore there must be some missing mass that we can't see. And we can't see it, so we've called it dark matter. So we know that it's there, but we can't see it, and we don't know in what form it is. So dark matter can't be seen, but it does make the density of the universe much higher and would explain why the galaxies spin so slowly. Now, okay, we know that the density will determine whether our universe will go on forever or whether it won't. And there's a certain cutoff point which says that if the density is higher than this certain amount, the universe will stop expanding and reverse, known as the Big Crunch. If it's smaller than a certain amount, the universe will expand forever and is called the Big Yawn. So it all depends on the density of the universe. Okay, so that's all of space recapped very quickly. But again, if you do want to look, revise, refresh, get notes down, it's on YouTube. So moving on to today's content, density. So density, a slab of concrete is much heavier than a slab of wood of the same size. So if we hold a slab of concrete, let's say 30 centimeters by 30 centimeters, and the same of wood, we know that the concrete is going to be much heavier. But why? They're the same size. Well, that is because of the density. So we know that the particles are much, much more densely packed in concrete than in wood. So we say that the density of concrete is higher than the density of wood. And we have an equation which allows us to work out density. And that equation is density equals mass divided by volume. And if you want it in a simple equation, then it's going to look something like this. Okay, so density is symbolized by this Greek letter rho. Okay, so it's a Greek letter, it's not a P. Very important because we're going to be looking at pressure soon. Not a P, it's a rho. So it's kind of like a curly P like this. Equals mass divided by volume. So I know density is not a D, it's annoying, but it's a rho in this example. Now, something that is very, very important about density is conversions. Okay, so we need to be really, really confident with our conversions. So we've got three different things. We've got density, mass, and volume. So we need to be able to know how to convert mass. So for example, if the question gives us a mass in grams, we need to know how to convert it into kilograms. The same if they give us a volume in centimeters, how do we get it into meters cubed, and the same for length. Okay, so you need to be very confident in our conversions. And if you need to, kind of knowing how many centimeters cubed are in a meter cubed. And then we can work out our density, which has the units of kilograms per meter cubed. So you know that the mass must always be in kilograms and the volume must always be in meters cubed. So let's go through this question quickly to make sure that we've understood the concept. So a wooden post has a volume of 0.025 meters cubed and a mass of 20 kilograms. What is its density in kilograms per meter cubed? So density equals mass divided by volume. Let's see, put your answers in the chat. What do you think the density of this wooden post is? What is the density of the wooden post using our new equation for density. So we're lucky in this question in the sense that they've given us the units. So density equals mass divided by volume. Mass is 20. Volume is 0.025. So if we do 20 divided by 0.025, we get 800. And that is measured in kilograms per meter cubed. So this question would probably be a 2-mark question. No unit conversion needed, just a simple division. So you'd get 1 mark for doing the division, 1 mark for getting the correct answer. That's kind of as simple as density gets. Okay, so how do we measure the density of a solid? Well, to measure the mass of the solid, we can just measure it on scales, that's fine, on an electric kind of balance. So we get the mass from just weighing it, but what about the volume? Well, to find the volume of a regular solid, we use our kind of normal formulas for volume. So if it's a cylinder, if it's a sphere, if it's a cuboid, we know all the kind of formulas for the volume of those shapes, and therefore we can find it just by taking a ruler, a micrometer, or vernier calipers, which are all different ways of measuring, depending on how big or small the object is. So if it's very, very small, we're going to use our vernier calipers. A little bit bigger, we'll use a micrometer. A little bit bigger, we'll use a ruler. And we can use base times height times length, or whatever formula it is that we need. Now that's only if it's regular, which is going to be quite uncommon because a lot of shapes are not regular in everyday life. So to find the volume of an irregular solid, well, it doesn't have a kind of perfect structure of a cylinder or a cube or whatever. It has a few kind of deformities. Then we need to drop it into water. Okay, so we're going to have a kind of beaker of water or some sort of container of water that will hold the object that we're dropping in. We're going to drop our object into the water slowly so it doesn't splash any water out. We're going to drop it into the water and we're going to measure the rise in the liquid. So before we drop it in, measure the liquid. After we drop it in, measure the liquid. And the rise in the liquid measurement is equal to the volume of our irregular solid. So this is known as a displacement can or a eureka can, or you can just say some sort of container of water. That's absolutely fine as well. Okay, so dropping it into a body of water and measuring the rise in the liquid will allow us to find the volume. Then we can just do mass divided by volume and work out our density. Okay, so we know how to measure the density of a solid, but what about a liquid? Well, we can use a measuring cylinder to measure the volume of the liquid by just pouring it into a simple measuring cylinder, or if it's a bit more, measuring it in a beaker. Then we need to measure the mass of the empty beaker on our scales. So we measure the mass of the empty beaker, take it off, pour the liquid in, measure it with the beaker with the liquid in. So now we have 2 different measurements, one with the empty beaker, one with the beaker with the liquid in. When we subtract those measurements from each other, we get just the mass of the liquid. Okay, so let's do an example of that question. So a measuring cylinder contained a volume of 120 centimeters cubed, of a particular liquid. So we know our volume is 120 centimeters cubed. Liquid was then poured into an empty beaker of mass 51 grams. But the total mass of the beaker and the liquid was then found to be 145 grams. So what is the mass of the liquid? So the empty beaker without any liquid in is 51 grams. The beaker with liquid in is 145 grams. So what is the mass of the liquid? What is the mass of the liquid? Put your answers on the chat. What is the mass of the liquid? It should just be a simple subtraction. Notice that it is in grams. So the mass of the liquid in grams is 94 grams. Okay, so the mass of the liquid in grams is 94 grams, but now we want to find the density. Well, we've been given the volume and we've been given the mass, but our volume is in centimeters cubed and our mass is in grams. So we need to convert into our proper units. So 94 grams in kilograms is what? Put your answers in the chat if you know. What is 94 grams in kilograms? 94 grams in kilograms. What do we need to do to the 94 to get it into kilograms? So 94 grams in kilograms, we need to divide by 1,000 so that we get 0.094 kilograms. So that's just dividing grams by 1,000. And then we need to get our volume into meters cubed. So this is where it gets a little bit more complex. So we have 120 centimeters cubed, but we need to go to meters cubed. Now the way that we do that is by dividing by 10 to the power of 6. So if we divide 120 by 10 to the power of 6, we get 1.2 times 10 to the minus 4. So to get centimeters cubed to meters cubed, we divide by 10 to the power of 6, or a million if that's how you want to remember it. So let's divide by 10 to the power of 6, and when we divide our 120 centimeters cubed by 10 to the power of 6, we get 0.00012 meters cubed. Okay, so now we have our volume in meters cubed and we have our mass in kilograms. So we have the correct units for our question, which means we can now move on to finding the density. So the density is mass, 0.094, divided by the volume in meters cubed, which we've just found to be 0.00012. Or your calculator might give you 1.2 times 10 to the minus 4, which is fine to go instead as the denominator. So when we divide them by each other, when we divide 0.094 by 0.00012, we should be getting a density of 783 kilograms per meter cubed. So that is how we do the conversion of units. Okay, so states of matter. We know that solid, and you should kind of know this from earlier on in your science education. So in year 7, year 8, or even year 9, you will have learned about states of matter. So solids, we know, have a fixed shape, they cannot flow, they have a fixed volume, and they have the highest density out of solids, liquids, and gases. Liquids fit the container that they're poured into. They can flow, they do have a fixed volume because they are contained. They have a higher density than gas, but a lower density than solids. Gas fills the container, it can flow, its volume can change, and it has the lowest density. So all kind of things that we should know, but just a little refresher. Changes of state. So what are the changes of state in my diagram here? Gas to liquid, liquid to gas, solid to gas, gas to solid, liquid to solid, solid to liquid. So we need to know what the names are when we go between each kind of change of state. So for a liquid turning to a liquid turning to a gas is evaporation, okay, or boiling. So that's a liquid turning to a gas. A gas turning to a liquid is condensation. A solid turning to a gas, so number 3, solid turning to a gas is called sublimation. Okay, so sublimation, it might be this new idea, which just means going straight from a solid to a gas, skipping out the liquid stage, going straight from a solid to a gas, and the same for a gas to a solid. When it skips out that liquid phase, and it goes straight from a gas to a solid, or a solid to a gas, that's called sublimation. So a new kind of keyword that we need to know. Okay, so 5, solid to liquid, it's just melting. And liquid to solid, that's going to be freezing. Okay, so these are our kind of key processes that we need to know the key terms for. So yeah, sublimation, evaporation, condensation, and melting and freezing. Okay, so now a kind of weird concept that you might not have thought of before. So the mass of a substance stays the same when it changes state. When an ice cube melts, the water it turns into has the same mass. If you leave an ice cube on a plate and you don't touch it, you just leave the ice cube on the plate, the mass of the ice cube becomes the mass of the water. There's no mass lost anywhere, and it might seem strange because if you think about holding an ice cube and the same amount of water, you do not think that they are the same mass, do we? And that is because of the density kind of playing tricks in our mind. When you hold an ice cube and you hold a bit of water in your hand, no way do we think that it's the same mass, but it is. If that ice cube melted into water, the mass of the water is the same as the mass of the original ice cube. So this is called the conservation of mass. And it's a weird concept that we've never thought of before, but it does make sense. Okay, so the kinetic theory of matter. This sounds really complicated and really like advanced, but it's actually not. All it means is that in a solid, particles are in fixed positions. We know that from when our teachers used to make us draw those annoying diagrams where we used to have to draw loads of dots, and in a solid they were nice and structured. So you might remember that. So in a solid, if we remember, the particles are nice and structured and are held in their fixed positions. Okay. And they keep their shape, they vibrate in that position and they keep their shape. They don't move, which is why a solid cannot flow. In a liquid, however, particles are in contact with each other and they move at random. They don't have their own shape and they can flow. In a solid, they have their own shape and they keep that shape. In a gas, they move much faster and much more randomly. They're much farther apart and less dense, so they can also flow. So it's really talking about the kind of particle structure and what that means for flow. We also need to know that the energy gets higher as we move through the states of matter. So particles in a gas have more energy than the particles in a solid. So the kinetic theory of matter is just talking about the particles and kind of how they are structured and what that means for flow and energy and vibration. Okay, so moving on to the last part of our content for today, melting and boiling points. So we know that when pure ice is heated and melts, its temperature stays at 0 until all the ice is melted. So an ice cube that is at 0 degrees does not change temperature while it's melting. Again, another weird concept that we've not thought of before. As the pure ice, so ice cube just sitting on a plate, is at 0 degrees. As it melts into water, until all of it is turned into water, it's still 0 degrees. Okay, so again, a really weird concept. We think that when something's melting, its temperature must change, but actually no, its temperature doesn't change until it's in its new state. Same for water being boiled. When water is boiled, its temperature stays at 100 degrees. So temperature stays the same during a change of state. A weird concept. Temperature stays the same during a change of state. Now, when a solid goes to a liquid, that is known as a melting point. When a liquid turns to a gas, that is known as a boiling point. That makes sense. We kind of knew that already. So we introduce these things called temperature time graphs, which allow us to see how the temperature changes over time for a specific material. So let's say that this is, a block of ice going through its journey. Starts off at 0 degrees at time 0, and it starts to melt. But as it's turning from a solid to a liquid, there's no change in temperature. So you can see that there's a change of state, but no change in temperature. It's a flat line. And where this happens is called the melting point. We can do the same from liquid to gas. So if we replace solid with liquid and liquid with gas, we will see the exact same curve. And where the change of state happens is where the boiling point is. So when it's doing that change of state process, the temperature doesn't change, and that is where we read off our melting or boiling point. You can see it in a different temperature time graph here. So for ice, we can see that it warms, someone's warming it, or the temperature of the room is warming it. Some kind of heat is working to warm it. Then it starts to melt. When it's melting, when it's turning into water, the temperature doesn't change. The water we might then put in a pan and boil it. It heats up, but until the water boils, when the water boils, it doesn't change temperature. It stays at 100 degrees. Okay, so a new concept. And this concept can also be known as latent heat. Latent heat is this idea that there must be some energy transfer to a substance to allow it to change state. So for an ice to change into water, it doesn't just do that automatically. There must be some energy to allow it to change state. So although there's no change in temperature, there is still some energy. We're going to look at this a little bit more in the next webinar, but it's this idea of latent heat, which gives the energy to change state, but does not give the energy to change temperature. So we've met quite a few kind of weird concepts today, and take some time to kind of digest them, think about them, and kind of get your heads around them. And we will go through latent heat a bit more tomorrow. I'm going to answer a few questions now quickly. So not too many questions, except what means what is meant by B times H times L. When I wrote B times H times L, all I meant was base times height times length. So the volume of a cube, really. Any other questions? Okay, someone said no, as some will evaporate if you leave it on a plate. Now that is absolutely true. So when we talked about the conservation of mass, so I said, okay, the mass of a substance kind of stays the same. When an ice cube melts, the ice cube turns into water and it has the same mass. Now that kind of lied to you a little bit. Some of that mass will be evaporated. Okay, some of the kind of water will be evaporated. We know that happens. We've all left cups in our rooms, and we've seen that if we've left it there for more than 2 weeks, which I definitely have, the mass of the water might start to get smaller, and that is because of evaporation. And that's fine. We know that evaporation exists, but we kind of account for it. It's not that much that we're losing. Okay, and when we're talking about these processes, we're talking about them in kind of a quick scenario. And so the mass that is lost for evaporation does need to be considered, but not in calculation. So they won't really ask you to account for the mass that is evaporated. Okay, so yes, there is the kind of consideration, but in calculations, don't worry about it. Okay, so let's go through some example questions then for the last 10 minutes. So the diagrams X, Y, and Z show that how the particles are arranged in 3 states of matter. Really, really, really kind of the most basic question that you can get in states of matter. Which one shows the arrangements of particles in a liquid and which one shows the arrangement of particles in a gas? In a liquid, we know that some particles are touching, but they're not really structured, and so that one must be Z. And for a gas, well, the particles don't touch and are quite spread apart, so we know that that must be X. So really kind of the most basic question that you can get. Okay, so in a gas, the particles move randomly. They don't move or they vibrate in fixed positions. And in a solid, the forces between the particles are what than the forces between the particles in a liquid. So let's deal with the first part first. In a gas, do the particles move randomly, don't move, or vibrate in fixed positions? Have a think, put your answers in the chat. What do you think happens to the particles in a gas? This question is all about the kinetic theory of matter, what we just did. So it's talking about how those particles move. So in a gas, they move randomly. In a solid, they vibrate in fixed positions. But in a gas, they move randomly. In a solid, the forces between the particles are stronger than the forces between the particles in a liquid. They have to keep those positions, so the force must be really strong. The picture shows a puddle of water in a road after a rain shower. During the day, the puddle of water dries up and disappears. This happens because the water particles move from the puddle into the air. But what is this process called? Is it radiation, evaporation, or condensation? Well, we should know by now that water particles disappearing means evaporation. So if we have a puddle, if we have a cup of water and we come back a few hours later, we might see that the water has started to dry up or started to lose mass. Now, what is one change in weather that might cause the puddle to dry up faster? So what might cause the puddle to drive faster? Would it be snow, windy, foggy, rainy, hotter, sunnier? What would happen? So for the puddle to go away faster, it would need to be hotter. And they would accept sunnier, but you want to be saying hotter. So change in temperature. Okay, explain in terms of the particles why gases are easy to compress. So have a think about this one. Why do you think gases would be easy to compress? Because of the way that the particles are spread. So why are gases easy to compress? Put your thoughts on the chat, then we'll discuss. So in a gas, the particles are spread out. There is lots of free space between the particles. This means that the density of a gas is low. And therefore, it won't take as much force to compress because there is this empty space between the particles. Okay, so most of the volume is empty space, and empty space is obviously easy to compress. So gases will compress much more easily because of this space between molecules. So the most important part that you get into your answer is there is lots of free space between the particles. Okay, so lots of free space between the particles. Okay, so we'll do this as our last question, just the first bit. The diagram shows the model that a science teacher used to show her students that there is a link between the temperature of the gas and the speed of gas particles. The ball bearings represent the gas particles, and switching the motor on makes the ball bearings move around in all directions. How is the motion of the ball bearings similar to the motion of the gas particles? Well, we know that the ball bearings move randomly. And that would be the key fact that you need to get in there. So when comparing ball bearings and gas particles, we know that they both move randomly. There is another question on the page. Do go home and, well, you're already home, but do have a look at that question and see if you can answer it for yourself after the webinar. So yeah, that's everything for today, and tomorrow we're going to be carrying on with density and states of matter.
Brilliant, thanks Preshayla. So if you join us for any other sessions, everyone, we have English literature, maths and biology today. If not, then see you tomorrow afternoon for the next physics session. And thank you Preshayla for today's session. So see you guys soon, bye.
Thank you, bye.